Hello, my name is Farah Alzafarani, and the topic I'll be presenting today is the efficient calibration of the NSLS2 gun cathode using machine learning. To begin with, NSLS2 is a research facility that has a storage ring that has an injector system. The beams that are produced are 10 times brighter than the sun, and the electrons travel at nearly the speed of light. NSLS2 has 29 experimental stations as shown by the diagram to the right. In NSLS2, there is an important program called the top-off program that maintains beam stability through the injection of electron bunches every minute. It attempts to compensate for energy loss due to the limited lifetime of the storage ring. However, there's a problem when attempting to calibrate the top-off program. Measuring beam properties for calibration consumes several hours, and beam dynamics involve nonlinear systems that are difficult to characterize. Thus, this inefficiency in calibration reduces time available for experiments. The research question I am attempting to answer today is how can the calibration process for the gun cathode or NSLS2 be optimized to improve beam stability while reducing measurement time? The purpose of the study is to utilize machine learning techniques to decrease calibration time, maintain a low standard deviation for accuracy, and provide stable and consistent light beams for experiments. This is because, as discussed before, the current method is time-consuming, traditional, and inefficient. To begin, I analyzed a calibration table provided by BNL, or also known as Brookhaven National Laboratory. This dataset includes variables such as voltage, pulse width, and charge. Using polynomial equations, I identified relationships among these variables. The goal was to create a baseline model, the truth equation, that would serve as a reference for evaluating other methods. This is a demonstration of the equations used to fit the data obtained from Brookhaven. The fourth order model, as you can see, is much more specific. Bayesian optimization was the cornerstone of my research. By leveraging Gaussian process regression and the upper confidence bound function, this method refined model predictions. Its purpose is to identify the most informative data points in order to minimize uncertainty. Then, utilizing those points, polynomials were created. I also tested random sampling, which involved selecting data points at random from the calibration dataset. Then, utilizing those points, polynomials were also created. Stratified sampling divided the dataset into intervals based on charge values, ensuring all ranges were represented. Once again, fourth-order polynomials were created from the points selected. Data collection was very important. For each sampling method, I created subsets of varying sizes ranging from 50 to 500 data points. These subsets were used to fit fourth-order polynomial models. To ensure consistency, each method was repeated 50 times, and the standard deviation of the errors was recalculated for evaluation. As you can see, the first thing I did was plot the original data set. The second graph shows the third order polynomial that was attempted to fit the data. However, it performed poorly. In contrast, the third graph, utilizing the fourth order polynomial, achieved an almost perfect match with the data. As shown by these graphs, the fourth order polynomial captured around 90% of the data within 0.1 of the standard deviation. On the other hand, the third order polynomial only captured 52% of the data points within the 0.1 of the standard deviation. For stratified sampling and Bayesian optimization, the p-value was below 0.05. Similarly, random sampling and Bayesian optimization, the p-value was once again also below 0.05, which means there was significant differences. However, the difference between stratified sampling and random sampling were not statistically significant because the p-value was well above 0.05. These results demonstrate that Bayesian optimization's superior accuracy is not due to random fluctuations but is real and reliable. When plotted, Bayesian optimizations consistently exhibited the lowest standard deviation across all data point intervals. Additionally, Bayesian optimization had the smaller bars throughout. In contrast, stratified sampling and random sampling began with higher standard deviations, and their error bars were significantly larger, particularly at the lower data points. Bayesian optimization also consistently achieved higher R-squared values much closer to 1 from the start. In contrast, stratified sampling and random sampling started with negative R values, only becoming positive after 150 data points. Negative R-squared values signify inefficiency and potentially deceptive results. Because the R value near 1 by Bayesian optimization, it confirms its capability for achieving an excellent fit with minimal errors. Significant differences in calibration times were observed as well among the sampling methods. Bayesian optimization only required 150 data points and 0.4 hours to achieve accuracy, compared to stratified samplings 500 data points and 1.2 hours, and random samplings 1.6 hours. This analysis highlights Bayesian optimization's superior efficiency in both data reduction and time. Thus, Bayesian optimization is the most effective method for calibrating the gun cathode at NS-2. It allowed me to efficiently identify the most relevant data points, reducing computational time without compromising precision. Compared to other methods, Bayesian optimization demonstrated superior accuracy and efficiency, making it a highly practical tool for optimizing complex models. The implications of the study extend beyond calibration. By freeing up more time for experiments, researchers can delve deeper into pressing scientific issues such as pollution analysis and soil contamination studies and advancements in nanotechnology. These improvements contribute to societal well-being and drive technological processes. Thank you, and these are my references.